little bit. Actually, to go back even more basic than that, and suppose we have an object that's being moved from point A to point B. You have a constant force F that's being applied to it. Then you may remember from physics, and it comes up from time to time in certain calculus classes, that the work done is force times distance. So in constant force, it's just going to be F times B minus A in this case. So that's the very simplest case. Now, if we make this a little more general, so we're still moving an object from point A to point B, but now the amount of force that's being applied to get the object from point A to point B is varying depending on where we are in between. So we can plot the amount of force as a function of x. So there's less force being applied here, greater amount of force here, and then less again. Then the way you compute the work in that case is you apply the simple formula for work on several subintervals with delta x. So here we have x1, x2, x3. So for instance, on this interval, the work is going to be roughly force evaluated at a certain x between here and here, times distance, which in this case would be delta x. So the total amount of work, so this ought to have been covered in 168. Of course, I find that I always have to say ought to when it comes to these things. Is the integral of the force from A to B. Okay. All right. So now this is what we're going to generalize so that it's a case where we're no longer moving an object in a straight line. We're now going to move an object along a curved path. So suppose we have some curve C with its initial point here and its terminal point here, and we're going to move an object along this path from point A to point B. Okay. So XA, YA to start, XB, YB at finish. Okay. So, similar idea to what we did here. You can cut up the curve, the smaller curves, and you can approximate the curve by several line segments. Of course, the more line segments you use, the more accurate your approximation will be. And we'll, yes?
Did you mean XAY? XAY?
Oh, that should be YA, yeah.
Point.
I take all of his
It
points.
would have been. Quick reflexes on your part. Okay. All right. So on each one of these segments of the curve, if the force is given by a function of f of xy for any point xy along the curve, then the work on this piece is going to be, and we call it W sub I, so we have segments 1, 2, 3, 4, and so forth, all the way up to segment n. Then the work is going to be roughly the force at some point on this segment. So it could be this point right here, xi star, yi star. So any point in a segment will do. Okay. So we get our force from that point, and then the distance will be the length of a segment, and I'll call that delta S I. So that's the work along each piece. Right. So the limit as the number of segments goes to infinity, the exact amount of work that it takes to move the object from point A to point B along its path, the way we write it, just for notation's sake, is so it's the integral over the curve C, maybe a function f ds. This is called a line integral. So it's going to be the limit as n goes to infinity of a sum of evaluations of a force. Please, no Star Wars references. Times the distance, the length of each segment. All right. Now we're discussing this in the context of computing work, but you can use the same idea, the line integral, to compute other things. For example, suppose the curve represents a wire, a thin wire with density rho as a function of x and y. Then, if we add up the density times the length of these segments, then what is it that we're computing? If we're taking density times length in this case because it's a wire, what is that going to give us?
Mass?
Yes. So, because we figured mass is being density times volume, that's for a three-dimensional object. But here we have, basically, conceptually it's a one-dimensional object, but it's a wire. And it has a density. So density times size, if you will, gives you mass of this wire. Okay. So this is how we define a line integral as a function over a curve by summing up the values of the integrand, the force in this case, density in this case, times the length of segments of a curve. But that's only useful to define what a line integral is. It doesn't really help you to actually evaluate it. So that's what we're going to look at now. And we can fall back on things that were discussed back in Calc 3. Now, if we take a look at one of these segments, so I'm going to zoom in on a portion of a curve. So here's the first point of the segment, xi minus 1, yi minus 1, and the upper end point is xi and I. And the length of this segment is this delta Si. That's the length of the segment that we're using to define our integral. Then what we have here is a right triangle. The legs are delta xi for this one, delta yi for this one. There's a difference in x values and a difference in y values. So that means that delta Si is square root of delta xi squared plus delta yi squared. So this is how we can relate it back to x and y. But there's still more that we need, more concreteness, in order to be able to actually evaluate the line integral. Even if we're given the function f of xy, we still need a more concrete description of the curve C. So we're going to assume that the curve is defined by